Hey guys, welcome back to another RASK maths video, and in this video I want to show you a really cool way of finding approximate solutions to differential equations such as the one you see here, using the Taylor series and the fact that with some initial conditions you can find a value of all subsequent derivatives at this point, and therefore create a Taylor series, which is an approximation for your actual solution when you have a small enough value. So what do I mean by this? Well, let's remind ourselves what the Taylor series is. When we have a differential equation, for example, when we have it in terms of dy, we're trying to find what y is in terms of x. So y is actually a function of x. Like, you don't see it, you usually just write it as y, but it's not its own independent variable. It's actually a function of x, which is why you can take dy by dx. If y wasn't a function of x, these two terms would be 0, so you'd end up with just y is equal to 1 over x, which is a bit weird, but also doesn't make sense. So let's remind ourselves how we could find y. Now, we have y of x. That's what we're trying to find. And we don't actually know what this is. Like, that is the solution. But what we do know is that using a Taylor series, and that's not specifically centered at x equals 0, which would be a Maclaurin series, but a Taylor series, we can rewrite y in terms of itself, its own derivatives. So this is going to be equivalent to y of a over 0 factorial multiplied by x minus a to the 0 plus y dash of a, over 1 factorial multiplied by x minus a to the 1 plus, let me see if I can go down, plus y double dash of a, so the second derivative of y evaluated at a, over 2 factorial multiplied by x minus a to the 2 plus y triple dash of a over 3 factorial multiplied by x minus a to the 3, on and on. If we went on forever, then this would basically be the same as the original y of x, and so we would have the Taylor series. If you stop abruptly, then it's just a Taylor sequence, or Taylor has a name, but I can't remember it. So yeah, let me actually do that in red. So you can see there's different ways of writing our solution, but this way here, the closed form, is definitely more preferable because it means like it's easy to work with. This is an infinite series, so it's hard to do calculations, and it's always going to be approximate, which is why we generally go for the closed form. But nonetheless, now that we have this, how can we actually form this without these random y dashes of a? Well, we already have these initial conditions here. So what we can do is, first of all, we have dy by dx, and we have y, and here, let me write, a is actually where the Taylor expansion is series. So you can see if this was a equals 0, this would be centered at x equals 0, which would mean all these terms just disappear. These will just become 0, and this is just a familiar Maclaurin series, which I'm sure you guys have worked with before. But we've centered at x equals a because here you can see our initial conditions are x equals 2. So we have to center this at x equals 2. Now, we know at x equals 2, y is equal to 1. So already we can put y equals to 1 there, and dy by dx is also equal to 1 there. But how are we going to figure out what y double dash and y triple dash are? Well, that's where this differential equation comes in, because we have x, y, and dy by dx. So this could go into there, this goes into there, and all of a sudden we're left with just an equation of d squared y by dx squared with a bunch of constants which you can rearrange. So that's the basic idea. We'll find all successive derivatives at x equals 2 of dy, and then we can just substitute them into all further terms. And this will give us an approximate solution for y, which we can then use to evaluate it within a certain radius of the of where it's centered. So therefore we can find an approximate solution to the differential equation without actually doing much hard differential equation work, which you might otherwise have to do, such as finding a particular integral, find a complementary function, things like that. So let's actually get started. First thing we have is I'm going to rewrite this as just 2y double dash plus y dash minus xy equals 1, where this is just a notation thing, y dash is dy by dx, just so it's easier. And now what I'm going to do is substitute these initial conditions into this equation so that we can get an equation of just y double dash. So after substitution, we'll get y double dash plus 1 minus 2 multiplied by 1 is equal to 1. And if you do some rearrangement, that gives you y double dash, which is d squared y over dx squared. That's equal to 1/2, 1's cancel out, and the 2 goes to the other side, so that's 1. So therefore, y double dash is equal to 1 at x equals 2. Remember this. Okay, now we've got this, and how could we work out what y triple dash is? Well, using this equation we have over here, we can use implicit differentiation and just get an equation with y triple dash, y double dash, and y dash all in terms of each other. So let's implicitly differentiate. To get 2 times, well, the derivative of dy by dx of y double dash is essentially, I should never written the y there, sorry about that, is the derivative of just d squared y over dx squared, which is just going to be, well, that's literally just d cubed y over dx squared. It's literally just taking it down in order, so we can write this as 2y triple dash plus y double dash, same thing. But as you can see here, this negative xy term is actually going to be a bit different because we have to use a product rule. Because remember, y is a function of x, so when we differentiate that, we have to use product rule. And it's not too hard. So leave this, differentiate this, leave this. So first bit's going to be y of x, and then differentiate this, leave this, so we get plus x times y dash of x. So overall, this new equation we have is going to be minus y minus x y dash. And when we differentiate left side, it's just 1, which is just constant, so that goes to 0. Okay, so here you can see we have a new equation with a new ordered derivative, y triple dash. And we already know what y double dash is, what y dash is, and y and x are. So we can substitute all that stuff into this equation and figure out what y triple dash is. So after substituting, we're going to get y triple dash plus y double dash, which is 1, minus y, which is also 1, minus x, which is 2, times y dash 1. That's equal to 0. And so after rearranging a little bit, we can get that y triple dash is going to be 1/2 multiplied by 2, which is 1. So we've got y triple dash of, remember, at x evaluated at 2 is equal to 1. So there we go. We've got our new solution for y triple dash at x equals 2. And as you can imagine, using this equation, we could literally just continue doing this, finding more and more successive derivatives, and therefore filling out more and more of this Taylor series until we get to the infinite Taylor series and we have our answer, which is exact. But I'm going to stop it here so that we have just a few terms, so it's an approximation, not the actual solution. So let's lay out all the information we have. X equals 2, y equals 1, y dash equals 1, y double dash equals 1, y triple dash equals 1, and we don't know the rest. It's not just ones. I think I can tell you that y quadruple dash is actually 1.5, so the pattern does stop, but let's just use these numbers for now. So we can actually write the y of x as its Taylor series over here. So let's start filling this out. We know the first term, well, a is actually 2. I'll just write 2 over here. So therefore, this first term is going to be y of 2, which we know is 1, over 0 factorial, which is 1. and x to the a to 0 is just 1. So this first term is going to be 1 plus y dash of a over 1 x minus 2. So that's just going to be 1 over 1 plus x minus 2 to the 1. Just leave it like that. The second derivative term, this is going to be y double dash of a, which is 1 over 2 factorial 2. So that's a half multiplied by x minus 2 factorial. So x minus 2 squared. And then we have plus y triple dash of a, which we worked out above, and then it's also equal to 1, and it's over 3 factorial. So that's 1 over 6 multiplied by x minus 2 to the 3. And you can see this would continue if we had more derivatives available, but we only worked it up to y triple dash. And yeah, now you can see we've basically got the the Taylor expansion at x equals 2. So what we can do now is, this is an approximate solution. If we cut off these terms, this becomes approximate. And this is an approximate solution to what y of x is. So we can use this to approximate, let's say, y of 2.1. Well, that is going to be 1 plus 2.1 minus 2 plus 0.1 plus 1 half 0.1 squared plus 0.1 cubed. And I actually don't know what that is and don't really want to do it in my head. So I can just use a quick calculator to figure this out. And that is actually approximately equal to 0.05. So you can see that we were able to find what values of y are past what the initial conditions have given us. And if you think about it, it makes sense, because you've given an initial condition and you've also given us some condition which the function might satisfy. So it makes sense that we can extrapolate this data to nearby regions and find what nearby points are. Like, as you can see, this is just above 1. So this point at x equals 2 has just increased slightly. Okay, so that's all fine, but where does this break? Well, you can see as these terms get more and more, the powers get bigger. If this is outside of, like, if x minus 2, the modulus of it is if it's greater than or equal to 1, then y of x will diverge. So we won't be able to get a solid answer. So therefore, this is the condition which we have, which is why we can only get answers to the differential equation or solutions within a certain radius. In this case, since it's centered around 2, this is only valid for when x is between 1 and 3. So yeah, that's the basic idea, and it's obviously going to get less and less accurate as you get closer to these bounds, because it's going to converge slower and slower. But yeah, that was the basic idea. That's how we can use a Taylor series to actually approximate what the differential solution equation is going to be without having to do heavy differential equation work. This seems like a lot, but if you had a really complex differential equation, such as the pendulum problem, I think it's something like this. I can't actually remember, but this is really hard to solve. I think it's near impossible. And yeah, we could find easy approximations by just differentiating and finding the derivatives at certain points. So thanks for watching, and I'll see you guys in a future tutorial. Bye.